Okay, so here we go. So, all right, so when we did momentum, one of the things that we learned was that you could describe, instead of thinking of force as being mass times acceleration, you could think of force as being the rate at which an object's momentum changes, all right? And I think I even told you guys that when Newton first wrote the second law, he wrote it in terms of the momentum of an object. And he said that the force was equal to the mass times the rate at which the velocity changes, mass times acceleration, which, if you rearrange stuff, this can be written as, instead of writing it as mass times the rate at which the velocity changes, you can write it as the rate at which mass times velocity changes, right? And mass times velocity is momentum. So our net force is merely the rate at which the momentum changes. Cool? So this chapter, we're talking about sort of the angular counterparts for all the linear stuff that we've done in the past. So basically, I'm going to kind of skip through the algebra here because I don't know that it's that enlightening. But basically, what it boils down to is, in the same way that sort of linear net force can be written as the rate at which the momentum changes, net torque can be written as the rate at which angular momentum changes. Okay? So where this becomes important, you guys, is this, and this will usually be the case. So in the case of force, if your force is constant, you get change in momentum equals net force times time, right? So notice that the direction in which your momentum changes, the direction of your change in momentum, is the same as the direction of your net force, right? In other words, if you're pushing something forwards, then the momentum is going to change in that direction. Follow? All right, so similarly, we can rewrite this equation for angular values, and we get this, that our change in angular momentum is equal to net torque times time. All right, so in the same way that the direction of the force determines the direction of the change in momentum, the direction of the torque determines the direction of the change in angular momentum. All right, we're going to talk about gyroscopic precession either late today or maybe tomorrow if we don't get to it today. But this idea right here is central to sort of why gyroscopes work the way they do. Okay, that the direction of the net torque determines the direction of the change in angular momentum. Cool? So that's going to be a big, big idea. All right. This little checkpoint here, I guess, is actually basically just review. One of the things we learned before was that net torque is your radius cross product with your net force, right? So take a look at the drawing here. So take a look at the drawing. So all of this is taking place in the XY plane. This, when I first looked at this, I thought F1 was coming out of the board, and it's not. So we've got, here's our origin, here's our point, and then we've got these four forces on it, and it asks you, which one's going to have the biggest torque, and which one's going to have a negative rate of change. So, I guess I kind of glossed over something here. It doesn't actually say which has the biggest torque. It says which one has the biggest rate of change of momentum. What's significant about that? That's the same thing as torque, right? So really, when I ask you, what's got the biggest rate of change of momentum, I'm asking you what's got the biggest net torque, right? So which one of these is going to have the biggest net torque? Yes, F3, right? Because all four forces are of equal magnitude. What's important about F3? Good, it's perpendicular, right? Okay. What one's going to be next? F1, right? And then what's the deal with the other two? Yeah, those do not produce torque because the angle between R and those other two forces is either 0 or 180. In other words, F2 and F4 are not going to cause any rotation, right? Follow? Okay, cool. Which one's going to give you a negative rate of change? In other words, which one gives you a negative torque? Let's see, we want negative would be pointing into the board. Wait a minute. Oh, right hand. Why is it not working? Yeah, right. Yeah, so that's true. Clockwise. Okay, everybody good? Does everybody see why F3 is the negative one? Kristen, you okay? Yeah? Yeah, Francis? For F1 and F3? No. That's what I was thinking too. Yeah, this isn't coming out of the board, so you'd have to split this up into components. And this component is smaller than the hypotenuse, so that's not a word, but. All right. Everybody good? All right, cool. So, long story short, we can now think of net torque as the rate at which the angular momentum changes. Cool? That was the point of all that. All right. Oops. Oh, there we go. All right, so then how do you find the angular momentum of a rigid body? Well, we learned last time that you can find the angular momentum of just a point particle by doing mass times r cross v, right? Okay, so basically, when you're looking at a rigid object, you're basically just going to sum this up over all of the objects. This is the slide I was thinking I was on, I'm sorry. Sorry about that. I'm going to change. Hang on a second, where's my notes? Lost my flow. Sorry, guys. Sorry, I'm just trying to see where we're going long term here. I think ultimately, this is going to be kind of a non-issue. So basically, here's kind of the gist of what you need to get out of all of this. I think this goes into more detail than what we actually need. So, like I was saying, to calculate the angular momentum of a rigid object, you just add up the individual momenta of each of the particles. Okay? And so if you want to find the rate at which the angular momentum of that rigid object changes, it boils down to the same thing. That the net torque on that object is going to be a measure of the rate at which the angular momentum of that whole object changes. All right. Notationally speaking, you guys, the lowercase l usually represents the angular momentum of a particle, and the capital L represents the angular momentum of like a solid object. But I've also seen the book kind of arbitrarily switch that up, so it doesn't seem like it's in stone. So kind of bear with me for a minute here. Once we get to the end of this, you'll see that it ends up being interchangeable anyway. So let's not get too tangled up about it, all right? So basically, this is the same thing we just had, right? Net torque is the rate at which your angular momentum changes, is basically what this is all telling us, okay? So, like I was saying, so to find your total angular momentum, you just total up the individuals, right? And remember, each individual one is mass times v times r, right? Right, that's the the equation that we learned yesterday. All right. What's up? Or Thursday, sorry. And then v can be written as omega r. Cool. So notice now I've got m times r squared times omega. But remember, mr squared is, and this is why I kept saying it doesn't really matter, mr squared is the rotational inertia of a particle. Okay? So, if I rewrite this as I, this is the only equation for angular momentum that I ever remember. L is I omega. All right, so let me say two things about this, and I think it'll give you a little bit more intuitive sense for what all of this means. I think I glossed through a lot of stuff here that ends up not being that big of a deal. All right, so check it out. Look, Regular momentum is regular inertia times regular velocity. Angular momentum is angular inertia times angular velocity. It's the same thing, right? Okay. Now, on Thursday, we spent all this time learning about particles. All right, well, suppose we've got a particle. Well, then it becomes this. L is, I for a particle is mr squared, right? So that's my I, times omega, right? Okay, well, this is mr, oops, not what I would do. Somehow I misspelled the M. And then what's r omega? V, right? So this is mRV. That's the equation that I gave you guys on Thursday, right? So if you understand this, honestly, that's kind of like the at the heart of angular momentum, is that one equation. Cool? And then if you divide both sides by time, so you do d. You take, I guess let's take the derivative of both sides with respect to time. Then that gives you the derivative of I omega with respect to time, which is the same as I times the derivative of omega with respect to time. What's dw dt? What's the derivative of angular velocity, guys? Angular acceleration. And what's I alpha? Net torque. Ah, everything fits together. Cool? So I'm kind of wishing that I hadn't gone through all that garbage on Thursday. I'm definitely going to change a lot. I'll probably do this next year. To me, this is really what you need to know. Good? All right. Here's the only weird exception. I think the only case in which you would need to know what we talked about on Thursday is if you had an object that was moving about some radius at an angle that was not perpendicular. Because then you have to go back to m times r cross v. So, all right, questions? Okay, cool. So, where's my little thingamajig for this? All right, so here we've got these three shapes. These are not intended to be sitting on a surface, so these are just like floating in space. Just this hoop, the sphere, they're just floating in space, and then you're going to put a force on it to change their angular momentum. All right? So it says, the disk, the hoop, and the solid sphere are made to spin about a fixed central axis like the top by means of a string wrapped around them, with the strings producing the same constant tangential force, in other words, they all have the same force on them, on all three objects. The three objects have the same mass and the same radius, and they're initially at rest. So we want to rank them according to the angular momentum, and then their angular speed, radius first. So, let's do A first. Let's see if we can figure out which one of these things is going to gain the most momentum as a result of these forces. Thoughts? The hoop, because it has the... Okay, so most inertia, most angular rotational inertia. Okay. So I agree, this one definitely has the biggest inertia. Which one has the smallest inertia? The sphere. And so this one's going to be somewhere in the middle, right? Okay, let's think some more. What else? Which one's going to be most affected as a result of that argument? Which one's going to be most affected by the force? The sphere, right? Because it's easiest to rotate. So the sphere is going to have the biggest angular acceleration, right? Which one's going to have the smallest acceleration? The hoop, which means that the disk is somewhere in the middle. So that argument it didn't help us a ton, right? Because the one with the biggest inertia has the smallest acceleration and vice versa. So I don't know if they cancel each other out, maybe they're all equal, I don't know. So we need to go about this a different way. About this. Which of the three shapes has the biggest net torque? They're all the same, right? They all have the same force and the same radius. So they have the same torque. So at any given time, they will have gained the same amount of angular momentum. They're all the same. They're all the same because of exactly what we said. The one with the most inertia is going to gain the least angular velocity, right? This one has a lot of inertia, but it's not going to gain as much velocity because it has a small acceleration, right? So A, all time. Which one's going to gain the biggest angular speed, though? That's the sphere, right? So this one goes sphere. That's going to have the biggest angular speed, right? Because it's got the smallest inertia, therefore the biggest omega. Followed then by the disk and then by the hoop. Make sense, you guys? All right. Any questions? If it helps you think of it at all, swap this over to linear. So we've got, I don't remember the order of my objects. This would be the same as a little object being pushed by some force, a big object being pushed by the same force, and a medium-sized object being pushed by the same force. Which one's going to gain the most momentum after time t? They're all the same, right? Because change in momentum is force times time. They've all got the same force, so after the same time, they'll all have gained the same momentum. But which one will be moving the fastest? The small one. Make sense? Everybody good? All right, cool. So, all right, so this brings us to the idea of conservation of angular momentum. Huge, huge idea. All right, so when we studied linear motion, we learned that if you've got a closed system, so that there are no forces coming from no unbalanced forces coming from outside of your system, then the total momentum stays constant. All right? No external forces, total momentum is constant. All right? So angularly, we have the same thing. In the absence of external net torques, then our total angular momentum stays constant. Cool? I realized, because I was going through my notes, I missed a parenthesis, so if this is going to bother you. Okay, so you guys have all seen the figure skater thing, right? What's the figure skater thing? Do you guys know what I'm talking about? Who's got relatively good balance and won't die if I spin them around on a stool? David, come on up. All right, can you sit on that and put your feet on the thing? I would prefer you didn't because I don't want you to split your head open. No. All right, can you hold 2 bricks out at arm's length? This one has dogs glued to it for some reason. It was the only brick I could find. Is that okay? You guys know anything about this? Anybody know anything about it? Dogs. Yeah, no, they're cute. All right. Okay, so if you kind of put their arms out, I'm going to spin you. You ready?
Yeah.
Okay, here we go. Okay, so right now he's got some angular momentum, right? When he pulls his arms in, what happens? Okay, let me speak a little harder. Torque. All right. So pull your arms in. Arms out. Arms in. Right? Every time he brings his arms in, what's he doing to his rotational inertia? Yeah, remember the rotational inertia doesn't just depend on mass, it also depends on the positioning of the mass, right? The reason this has more inertia than this is because this has the mass farther out. So right now, with his arms out, David is this, and then when he pulls them in, he's this. Whoa! All right? So, thank you. All right? So the idea is, with your arms out, because the mass is far out, you have a lot of inertia, right? When he brings his arms in, what he's doing is he's decreasing his angular momentum. I said that wrong. Decreasing his rotational inertia. I'll write it down on the board in a minute. He's decreasing his rotational inertia, but his momentum has to stay the same. And so the angular velocity gets bigger to compensate. Let me write it down because I did a rough job saying it. All right, so this is like the classic example, the figure skater example. All right, so here's our figure skater. Those are ice skates. Arms out. Spinning. Right? Then, when the figure skater pulls his or her arms in, all right? So the idea is, in both cases, he turns into an angel, exactly. Right, look, he's got the same angular momentum. Angular momentum is I times omega, right? So over here, with his arms out, he's got mass distributed far from his center of mass. So he's got a large inertia and a small angular velocity. When he pulls his arms in, what he's doing is decreasing that inertia. And the result is, well, if I got smaller, then omega must get bigger to compensate, right? Follow? Had you guys not seen this? Did you guys not learn this last year?
Yeah.
Don't know? Okay. All right. I should have, if I'd been smart, found a video of a figure skater. That would have been smart. But I figured this kind of shows the same thing.
I was pretty good. I really like this notation, like big letters and small letters.
Yeah, that's a thing from Hewitt. All right. Good, you guys? Now notice, when David did this, think about the bricks for a minute. So the bricks are moving this way, right? What direction is the force that David's exerting? Inward, right? And where's the radius? The radius is the arms, right? So the force is inwards along the radius. So what's the torque he's producing when he pulls them in? There isn't any, right? There's no torque, right? Because the radius is this, and the force is anti-parallel to it, right? Okay? Make sense? Furthermore, even if he was producing a torque, it would be an internal torque, right? And so it wouldn't necessarily change the momentum anyway. Good? All right. So this ends up being why the spinny the wheel spins. We'll talk about that in a minute, but I want to do some examples first. For whatever reason, your book is really big on the rhinoceros beetle. There are, and I'm not exaggerating, probably 10 different references to the rhinoceros beetle. And it's always about this. I assume, I didn't Google it because I haven't had time. I'm assuming the rhinoceros beetle is a relatively large bug. But he's always on a record player or a disc that's rotating around. I don't know. Whatever.
What if it's the same beetle?
I
Question.
don't know. It's a good question.
We should name a beetle.
Well, oh, did you just Google it? Really? I'm sorry. All right. So I'll tell you what.
Oh, it's like the one from Bugs.
Oh yeah. Oh, all right.
Sorry, I just got really excited.
Yeah. What's his name? Do you know?
No. I'll look it up.
What do you got? Resnick? Oh, I got you. I was going to say, that's the name of...
What's Haliday?
Yeah. All right. So, check it out. So this example here is exactly the same thing as the figure skater, all right? So it says a rhinoceros beetle rides the rim of a small disc that rotates like a merry-go-round. So here's the merry-go-round, here's the beetle. Okay? So right now, the rotational inertia is the I of the disk plus the I of the beetle, right? Right? Now, if he crawls towards the middle, what's going to happen to the overall rotational inertia? Rotational inertia. It'll be less, right? So what should happen to the speed that the record spins at? Should go faster, right? But the angular momentum should stay the same, right? Okay. So what happens to the rotational inertia? It should decrease. What happens to the angular momentum? It should be constant. What happens to the angular speed, or as a result? It should increase. Does that make sense, you guys? All right. So most of the problems, you guys, basically are this. L initial times omega initial. No, wrong. Sorry. L initial equals L final, right? Starting angular momentum equals ending angular momentum. I guess I should put a sigma in front to indicate total. So that means that I initial times omega initial plus, no, not plus, sorry. Man, I'm struggling. Equals I final times omega final. That's how most of these problems are going to be set up. You're going to have enough information to know both your angular velocity and your rotational inertia at the beginning. Then the rotational inertia will change and you'll find the final angular velocity. Cool? So let's do an example with numbers. What's up?
Dim.
One more time?
Dim.
Dim. Oh, okay. DIM.
Yeah.
Sad.
I know, I was expecting something really good. Like,
It doesn't make him sound very smart either. All right. Also, incidentally, there's a typo in here that I meant to change. I deleted half of something, but no. Nice try, though. I deleted half of something, but forgot to finish it. So it says in a playground, there's a small merry-go-round of radius 1.2 meters and mass 180 kilograms. And then across the software, it says its radius is 91 centimeters. That was going to be a reference to something different that I deleted and didn't completely delete. Okay. And then there's a kid with a mass of 44 kilograms. He's going to run at a speed of 3 meters a second along a path that's tangent to the rim of the initially stationary merry-go-round, and then he jumps on. So, neglect friction between the bearings and the shaft of the merry-go-round, calculate the rotational inertia, blah, 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 blah. All right, so here's our picture. So initially, we've got a merry-go-round with an angular velocity of 0, and we got a kid who's going to run and jump onto the thing. Okay? After, we're going to have a merry-go-round and a kid spinning together. Does that make sense? So the kid runs and jumps on. Basically, it's an completely inelastic collision, right? Yes. The kid sticks, exactly. All right? So, let's write an expression for what's going on initially. So, our total momentum initially is the momentum of the merry-go-round initially plus the momentum of the kid initially, right? So, what's the angular momentum of the merry-go-round initially? Good. Why is it 0? Because it's not moving, right? Angular velocity 0. Plus the angular momentum of the kid. Well, let's see. That's I omega. So what's I for the kid? That's mr squared. So let's see. His mass is 44 kilograms. This is a dumb way to do it. I'm sorry. Because I don't know my omega, right? So,
Isn't omega just WR?
yeah. So this is basically MRP. A better way to do it. So good. So what is the radius? So the radius is always, I shouldn't have shrunk my drawing. I'm going to redraw this. So here's the merry-go-round. Here's the kid. About what point is our system rotating? the center of the merry-go-round. And the kid's jumping on at this point. So r is the radius of the merry-go-round. Does that make sense, everybody? Okay. And is everybody okay with how I got this MVR? Remember, I omega is the same as MVR. If you replace omega with mr squared, and v is omega r.
Yeah.
All right, cool. All right, so we get 44 kilograms times 1.2 meters times 3 meters a second, right? Cool? So what's that give you? This isn't the way I did this in my notes. I didn't write that number down. Oh, yeah, I did. 158.4. Equals 158.4, and it's kilogram meters squared per second squared. All right, so that's how much angular momentum the system has before the kid gets on the merry-go-round. Cool? Now, after the kid gets on the merry-go-round, do that in blizzard. Total angular momentum final. Well, that's the momentum of the merry-go-round final plus the momentum of the kid final. So that's I of the merry-go-round times the angular momentum final plus I for the kid times the angular momentum final. Ah, dang it. What should be true about the two angular momenta? They should be equal. Oh wait, did I say that right? I didn't say what I wanted to say. What should be true about the angular velocities? That's what I find out. They should be the same, right? So this is I of the merry-go-round plus I for the kid times the final angular velocity, right? Make sense? All right, so I don't know if you guys remember one of the things I commented on when we were learning about rotational inertia. I said you can just add them. Here's another example of that, right? You're just literally adding the two angular momentum. Oh, God, I can't talk about it. You're literally just adding the two rotational inertias and treating it as one object. Follow? Okay, so I for the merry-go-round. Well, it's a disk, right? So that's 1/2. The mass was, what was it, 180? And then its radius is 1.2 meters. Don't forget to square it. Plus, how do I find the rotational inertia for the kid? mr squared, right? So that's 44 kilograms times 1.2 meters. Don't forget to square it. So that's I. Why is so much cold energy? This kid's not the smart board. I don't remember this being an issue in the past. Alright, times omega f. Good or no? Alright, so what does that giant mess there in the parentheses give you? It gives you 192.96. So this is 192.96 omega f. And that's wait, say that again? Yes, exactly. Exactly. All right, and so, like Alex just said, the whole premise behind this is our total initial angular momentum ought to equal our total final angular momentum, because there are no external torques being provided to the system. So now we're done, right? We can solve this. So let's see. So that means that 158.4 equals 192.96 omega f. Solve, and your omega f is 0.821. What units do you think it gives you? Radians per second. Yeah, exactly. All right, so now how do I find the kid's velocity? Just use a jumper, right? So that was parts B and C, A, B, and C we just did there, right? A was this. A was the rotational inertia, B was the angular momentum, C was that velocity there. All right, D says what's the angular speed going to be if he crawls halfway to the center? So how is that going to change this mess here in blue? For part D, sure, what do you got?
You change the kid's radius to half what it is now.
Yeah, exactly. This just becomes 0.6, right? And then you solve it again. All right. So this was question C. Question D, what Tony said is exactly right. You just change this to 0.6. So very good, sir. So question D, if you solve it, you end up getting 1.09 radians per second. Why am I happy that I got a smaller number? Or a bigger number, sorry. Why am I happy that I got a bigger angular velocity? Less inertia when you're closer to the center, right? So it spins faster. Cool? Questions? Alrighty. All right, so let's do this. This example's crappy. I went through it at lunch. I don't like it, so we're not even sure. All right, let's talk about gyroscope. So here's the deal. I don't have time to give you a good explanation of this. So here's what I'm going to do. I'm going to show you, and then I put on my website 3 videos. I want you guys, this is your homework tonight. Watch videos. One of them's like 3 minutes, one of them's like 6 minutes, and I don't remember how long the other one is. They're all pretty short. Okay? So watch the videos, and then we'll talk tomorrow and answer questions, okay? So, first of all, to get to the videos, if you go to my website, Hecker Stuff, over here on the side, hey guys, oh shoot, over here on the side under the number of days to the AP test, yikes, 56. Hang on. All right, so over here, oh no, I forgot to add it. All right, I will add it before you guys leave. Right here, it'll be under light. It'll say it's for session, and there will be 4 videos you can watch. All right, at the very least, watch the first 2. Okay? Man, so here's the demo. I think you guys saw this last year, so this won't be mind-blowing.
I think I know this is off the line.
Am I right? You guys have seen this, right?
Yeah.
All right, so you guys ready?
Yeah. Max, spin it.
No, that's it. Oh, that's high.
I was like, that's not what I was saying. What's your turn?
Yay, right? Okay, so the videos talk about why this happens. The first one gives you the rationale that I've always learned, which is the right-hand rule thing. The second one I had never seen before, and honestly I'm still trying to wrap my head around it, but it's a little bit more of an intuitive explanation for why this happens the way it does. And it explains why it's rotating this way, as opposed to the other way. Right? Did I changed it, right?
Yeah.
Cool? All right, so watch those 2 videos. It's like 10 minutes. We'll talk tomorrow, all right?
No, it's just the way
Weird. I would be lying if I said that I 100% understood. I meant like 80%. All right, guys, have a good day. You too.
If you spin it right now, while it's like that. Nothing.
Yeah, no.
That's not fun.
A little bit of friction
Yeah.
winds the rope up, but
Right, move in.
Not the other way, but full attention.
what do you mean?
I don't know.
Spinning it this way, you mean? No, I mean,
I mean, like, it shouldn't do
Yeah,
anything.
theoretically.
It's not gonna, like, go.
if it was totally frictionless, then it shouldn't wind the rope at all. It doesn't have anything to do with the direction it's spinning in. But there's a little bit of friction.
No.
Snow now.
Are we supposed to get more snow tonight? Really?
I don't like the snow, go away. Mark.
I agree.
Think,
Oh, sorry.
think
Let's
it's
go,
just
Mark.
Yeah, see you guys. See ya. See you later. Oh, I need to do the thing, don't I? Let's see. Oh,